Hello, in this little series of videos, we're going to be talking about a couple of simple examples of matrix groups, namely the groups denoted by SO2 and O2. Now, I realize there's a little bit of a glare on the board over there, and I can't do anything about it because the windows are like 15 feet high, but it doesn't cover anything that we're going to need in this first video. So these groups here, SO2, what this notation stands for is special orthogonal group. And of course the 2 means that it's the second one, so I could put a little second up here. And of course I'll tell you what these words mean later. And then O2, as you might expect now, is just orthogonal group without the special, and there is a second here, so it's the second orthogonal group. Now I can tell you in very simple terms right now what these groups do, what they are, what they do. And so if this is the plane, so this is the Euclidean plane, this little blue plane here, what the orthogonal group does, this one here, is this is all distance preserving transformations of the plane. And by the plane, I mean the Euclidean plane R2. So R2, that also preserve a fixed point. Now that's kind of a mouthful, and that's why I have this little plane here to illustrate for you what this means. So if you start out with the plane like this, and I have drawn a coordinate system on it, then you can transform it, which means you can move it around. Now theoretically, you could also stretch it, like pretend it's a piece of rubber or something. You could stretch it or shrink it or twist it or whatever. Now that's not allowed because this says distance preserving. So we're looking at very simple transformations that preserve all the distances. And that means that if I have 2 points, say I have this point here in the center, and then I have the end of this little arrow point here, well, I have to transform the plane only in ways that will preserve those. So if this was a piece of rubber, I would not be allowed to stretch it like that. I would, well, there's only a couple things you can do. You can either rotate it, so you can rotate it around like this, or else you can flip it over somehow. Now, that restriction to rotations and flipping it over, which I'll call reflections, that is where this business about preserving a fixed point comes in. And see here, this fixed point is going to be this point here I put in the center. So the idea is you fix that point there, and then you're allowed to rotate it. You're either allowed to rotate it, or else you're allowed to flip it over in some way that leaves that point where it was. So I could flip it over like this, provided that this point here stays in the same place. Now that's all that the orthogonal group O2 can do. Those are the only transformations it's allowed to do. It can either rotate, keeping this point fixed, or else it can reflect somehow. Now it could reflect in different ways. For instance, it could reflect like across this vertical line. I could take it and flip it this way, and it would still preserve that point. Or I could reflect it across the horizontal line, take it and flip it that way, and it would still preserve this point. But that's what this group here is. Now let me set this over here and get it out of the way. What SO2 is, now this is an additional little condition because it says special orthogonal group, not just orthogonal group. And so what this one here does this is just rotations about a fixed point. So once again, grabbing my little plane over here, it's just the ones that rotate. So what the special does is it kills off the reflections. It means you're not allowed to reflect it anymore. You're only allowed to rotate. So that's a very concrete geometric description of what these groups are. You can really understand them. And so you could call these sort of like, cute little matrix groups. Because they're nice to you. They let you understand them in an easy way. These are the kind of matrix groups where if you were on a long transatlantic flight or something, you would want to cuddle with them, right? This is how you should feel about these matrix groups. Now, of course, I'm being just a little bit sarcastic, but these are things which are not difficult to get a grasp of in terms of what they do. And so we want to start with something concrete like this. Later we'll be talking about matrix groups that you can't visualize as easily as what you can with these here. Now in this first video, having just told you this little bit of introductory stuff, the only other thing I'm going to do is show you an example of a rotation matrix, which is one of the elements of this SO2 group, the special orthogonal group. Now the SO2 group is a subgroup of the O2 group, so you would write that like that. That this one is contained in this one here. It's like this one plugs into this one here. So this matrix here is also an element of the orthogonal group. It fits in this one, and then this whole group is a subgroup of this one here. So I want to just show you, look at this example of a rotation matrix and show you how it rotates things. So let me clear this off. Okay, so we're going to look now at this particular rotation matrix, and I'm going to just copy it here so you're looking at it in the same place. So there's a square root of 3 over 2 here, and then there's a minus 1/2, there's a 1/2 here, and then there's a square root of 3 over 2 here. And so this is a 2 by 2 matrix. And of course, it will turn out that all of the matrices in SO2 or O2 are 2 by 2 matrices. That's what the 2 means. All right, now what does this rotate? So this rotates column vectors in the plane. Now, I'm not really assuming you know much. I mean, I'm not assuming you know linear algebra, for example. And we talked before about matrices and how to multiply matrices. But let me just identify for you or remind you what these column vectors are, or how you can think of them. So these column vectors are, so what a column vector, these are 2 by 1 matrices, and so they look like this. So remember that 2, the first number is the number of rows, the second number is the number of columns. So you'll have some A and some B here, and here A and B are real numbers. You remember this symbol means is an element of, so this means that A and B are in the real numbers here. So the way you think about these geometrically is as arrows. But this is one way you can think of them. And so what you do is you draw a copy of the plane. and then you draw an arrow. And this arrow, so I can draw this arrow, and then I can draw a perpendicular line here, and this is a right angle. And this distance here is the A, and this distance here is the B. So what the AB means is it means this arrow here that points to that point in the plane, which has, you know, if you like, you can put an X coordinate here and a Y coordinate here, and then you can say, well, this is telling you that it's the vector that points from the origin here to the point that has X coordinate A and Y coordinate B. That's a way you could say it. So what we want to do is we want to take some of these vectors and see what this matrix does to them. Now, the way, when I say does to them, what I mean is that you're going to multiply using matrix multiplication, which you all know how to do now very well. You'll multiply this matrix by this matrix. It's a matrix. It is, we call it a column vector, but it is a matrix, and we'll see what it does to it. So we'll say that the matrix, let me see if I can fit this down here. The matrix, and that's this matrix here, it acts on, so it acts on column vectors by matrix multiplication. I'll just write mult there, it means multiplication. I won't be able to fit the multiplication there. And so what does this mean? What it means is you start out with a column vector, AB, and then you send it to, that's what this little arrow means. It means it maps this thing over to this other column vector, which is going to be the matrix. Times the original column vector. Now, if I have room down there, I could write out what that matrix product was, but I'm not going to, because we're going to use some specific examples where I'll choose a particular A and a particular B, and I'll show you how this thing rotates those vectors. Now, in this video, I'm not going to prove anything. I'm just going to pick a few vectors and show you how it actually works. So what I'm going to do is I'm going to clear off all of this stuff down here. I've been talking about column vectors, and then we're just going to choose a few particular column vectors and see what happens to them when you multiply by that matrix. So let me clear this off. All right, so this first example will be, we're going to rotate the vector, and we'll just choose the one that is 1, 0 first. Now, this vector, so the way this vector looks, I'll just draw it over here. I'll draw a little coordinate system over here. You remember the 1 here, this was the A, and the 0 is the B in this case. Well, the 1, that's the X coordinate, so if I put X over here and then Y up here, then that would tell me that I'm coming out 1 unit in the X direction and 0 units in the Y direction. So that's just a little arrow that points from the origin over to this point, so that distance there is 1. And the I don't know why I write my 1 here like this and this one without the little ornaments, but anyway, that distance is 1, and then the vertical distance is 0. So this is the vector that we're starting out with. So what we're going to do is we're going to take the matrix, square root of 3 over 2 minus 1/2, 1/2, square root of 3 over 2. And we're going to take this 1, 0, and we're going to do the matrix multiplication. So what will happen? Well, you remember just from talking before, this was a 2 by 2 matrix. This is a 2 by 1 matrix. The product is defined because these middle numbers here agree. And the resulting matrix will be a 2 by 1 matrix because those are the outer numbers. So you remember this. And so 2 by 1 will mean that it's once again going to be a column vector as we think of it. So what's the first entry going to be? This is, to get that, we take the top row here and we pair it with this column. We multiply this entry by this entry, this entry by this entry, add them together. That gives us just a square root of 3 over 2, because this minus 1/2 multiplies with the 0. That doesn't make any contribution. And then we have the bottom entry, and so that gives us a 1/2 multiplied with the 1, and then square root of 3 over 2 multiplied with the 0. So that just gives us 1/2. Now, the way this looks, and maybe I'll doctor my picture here so I can fit in this one here nicely. Is it has taken the, now the x component is square root of 3 over 2, right? And so what is that, 0.866 or something? You can put it in your calculator. So you can see that this looks like something like this now. It's going to be, so you're going to have, if I want, I can draw my little perpendicular here. And then this distance is going to be square root of 3 over 2. And that distance there is 1/2. Now, you can sort of see visually what's happened. It's taken this vector here and it has rotated it. Now, what this will amount to is a rotation by, if you think about radians, it will be pi over 6 radians. If you want to think about degrees, it will be 30 degrees, whichever way you want to say it. And this is, it's counterclockwise. So it's starting the vector out here, and then it rotates it up like that. Now, how do I know that it's just rotated it, that it hasn't stretched it or shrunk it too? Well, if I wanted to know what the length of this vector is, so I want to check that the length is still 1. Because otherwise it wouldn't just be a rotation. And so that's just the Pythagorean theorem. You want the hypotenuse here, and you have this side and this side here. So what the length is it's just the square root of the sum of the squares. So that would be square root of 3 over 2 squared plus 1/2 squared. And then this is going to be the square root. Well, that square root of 3 over 2 is going to square to give me 3 over 4. And that's going to square to give me 1 over 4. So that's going to end up 3/4 plus 1/4 square root of 1, which is 1. So it still does have unit length. All it's done is taken it and rotated it by 30 degrees. Now, you could say, okay, well, this matrix rotates that particular vector by 30 degrees, by pi over 6 in the plane. But how do I know that it will rotate every vector that way? Because if it doesn't, then there's no justification in calling it a rotation matrix. So let's choose another vector and see what happens. And once again, I'm not proving anything. I'm just showing you some examples. So I'm going to rotate this vector now, 0, 1. And so the way this vector looks is, here's x, here's y, and this is just the vector that points straight up like that, and that distance there is 1. Because the x component is 0, it doesn't have any component pointing in that direction. So we're going to take the matrix square root of 3 over 2 minus 1/2, 1/2, square root of 3 over 2, multiply it, 0, 1. Watch what happens. This first row, it picks out a minus 1/2. The second row here, it picks out a square root of 3 over 2. That's the vector you get, and the way this looks, that's messy. The way this looks geometrically is the minus 1/2 tells me I come out a distance of minus 1/2, and well, 1/2 in the negative direction for x. So this is x and this is y still. And then I go up a distance of square root of 3 over 2. So that's telling me it's a vector that goes like this. And so I could draw a perpendicular line there. This distance here is square root of 3 over 2. That distance there is 1/2, and the minus comes from the fact that it's going in the negative direction here. So you can see the same thing happened to this vector geometrically. It started out pointing this way, and then it rotated 30 degrees this way. So it's that same rotation happening. And we'll do one more. So let's just choose some kind of random looking one. Let's look at, say, 1 and 3. So here the scale is going to be a little bit different on my picture because it's a bigger vector. Let me redraw this. So we're kind of zooming out here because I want to draw a coordinate system that looks the same size but have a bigger vector there, so we have to zoom out the window. So this says we're going 1 unit, let me draw little tick marks here, 1 unit in this direction and then 3 units up. So the way this vector looks is like that, and I didn't quite do it accurately. Let me fix this here. All right, so this is going to go up like, that's a bit better. And so I could draw, if I wanted to, I can draw a perpendicular line that goes down there. And then this distance is 3 up, and that distance is 1 going that way. So let's see what happens to this vector here. Well, I'm going to multiply it by the matrix again. And what is this going to come out to now? Well, I'm going to have a square root of 3 over 2 coming from this. So this is going to be, and this is kind of messy because we have a square root of 3 over 2. And then we have a minus 3 over 2. And then down here we have a 1/2. And then this is going to give me plus 3 square roots of 3 over 2, provided I did that correctly. Now, you know, it's not obvious from these numbers, I guess, that the rotation is exactly 30 degrees, but it's at least believable that that's what it comes out to be. Because you can see 3 over 2 is bigger than square root of 3 over 2. So this minus here will make this be a negative amount, but not a very large negative amount. And then you have this amount here, whatever this is. And so this is going to come out looking something like this. It's going to be slightly negative in this direction, and then it's going to be mostly going up here. So once again, you see that sort of rotation. You know, it started out, maybe it started out like that, and it's rotating 30 degrees. Now that might look like it's symmetric about the y-axis. It's not in this case, but anyway, it goes a little bit beyond the y-axis when it rotates that way. So you can at least see what's happening. You can see what the machinery of this is, and it should at least be believable or plausible to you that that's what this matrix is doing, that it's taking each vector and rotating it. Now what you should do is you should make sure, for instance, you should make sure that the length of this vector is the same as the length of that one. because otherwise it won't actually be a rotation, but I'm not going to add additional minutes to the video by working that out. So in the next video, we'll talk about rotation matrices in general, and that's this part here.